The purpose of this lab is, by making an experimental setup that compensates for Earth's magnetic field, to establish the distance relationship for the magnetic field produced by a small bar magnet and calculating its magnetic moment, and compare measured values for off-axis field magnitudes with predicted values found with a computational model that simulates a bar magnet with the magnetic moment found through the experiment. The main principles involved in this lab are the general Biot-Savart law, the magnetic field of dipole on axis, and the distance dependence formula of a bar magnet, as well as the field produced by a magnetic dipole. The distance dependence relationship for a bar magnet was found experimentally, establishing that the magnitude of the magnetic field is proportional to a constant which is very close to the value established by the Biot-Savart law, and the magnetic moment of the magnet was calculated with this value. Lastly, the distance at which the net magnetic field of axis on the sensor is 100 microteslas was measured and compared to the expected value using a computational model differing significantly. Assuming that the magnetic field due to a bar magnet is proportional to some power of the distance, we can write the following distance dependence relationship, where k is a combination of constants. Through the general Biot-Savart law, we can find the magnitude of a magnetic field due to a magnetic dipole on axis by simplifying the expression. Equating this expression to the distance dependence formula, we can derive an expression for the magnetic moment of the bar magnet, and by doing a simple experiment, we can find the value for this magnetic moment. In this setup, the system is the magnetometer in the phone, while the main elements of the surroundings are the bar magnet on the Earth, which produce a magnetic field at the location of the magnetometer. First, we align the meter stick east to west and place the phone perpendicular to the meter stick. If the alignment is good, the phone should be the magnitude close to the net magnitude field at the location where the experiment is. Then, if we place a magnet in front of the phone and slide the phone along the meter stick, we can find the position of the meter stick by measuring where the magnitude in the x direction is maximum. Similarly, we can rotate the phone 90 degrees and do the same method, by this time maximizing the magnetic field magnitude in the y direction. Once the experiment is set up, first we place the bar magnet on axis with the magnetometer, and after that we slide the magnet along this axis until the magnitude of the magnetic field measured by the magnetometer is 20 microteslas. We record the distance, referred to as R20, from the magnet to the magnetometer. For this experiment, we took 3 measurements each for the distances R20, R70, R120, R170, and R220. By taking the natural logarithm of the distance dependence relationship we established earlier, if we take the natural logarithm of the magnetic field values and plot them against the natural logarithm of the recorded distances, we should get a line. Thus, we can establish the values for n, the slope, and for the natural logarithm of k. By doing so, we obtain the following plot. From the plot, we get the following values for n and k. Using these values, the distance dependence relationship, and the equation for the magnitude of the magnetic field on axis for a magnetic dipole, the established magnitude of the magnetic moment of the bar magnet is. We should note that the value for n is extremely close to that dictated by Biot-Savart law, indicating that the experiment is valid. Now, with the same setup, we now measure the distance at which the net magnetic field is around 100 microteslas when the magnetometer and the magnet from an angle of 45 degrees. We do so by placing the phone and the magnet as indicated in the diagram. The value should then be corrected to account for the Earth's magnetic field. We can now do a computational model that replicates the experiment. First, we set up the constants and create a cylinder object that replicates the magnet. Next, we define a function for the magnetic field of a bar magnet at an observation location. Then, we define observation locations based on distance. After that, we create arrow objects for the magnetic field on axis and perpendicular to the axis. Finally, we define the magnetic field 45 degrees off axis. Both we get the following results. It is clear when comparing the magnetic field magnitude at 45 degrees at a certain distance that the magnitude calculated by the computational model differs significantly by the magnitude shown in the tables, which is the magnitude obtained experimentally. Some observations include that when the magnetometer is far away from the magnet, it measures a near zero magnetic field in the x direction, and as the magnetometer moves closer to the magnet, the measured x component of the magnetic field increases, and the position of the device is significant, as the effect of the magnetic field produced by the Earth must be minimized to carry out the experiment successfully. Some sources of error include that the position of the magnetometer found during the experiment may be slightly off, the reading of the magnetometer of the Earth's magnetic field at the start of the experiment may have been incorrect, other nearby sources not accounted for in the surroundings could affect the magnetic field measurements, and the distance measurement errors between the magnet and the device could impact the distance value. If we hadn't aligned the phone to account for the Earth's magnetic field, the experimental results would be less accurate due to the fact that the Earth's magnetic field would have to be accounted for by subtracting its contribution to each of the components for the total magnitude for each component. And if two identical magnets would have been together end to end, the magnitude of the magnetic field would increase as the fields produced by each magnet will be pointing in the same direction. In this experiment, it was found that the distance-dependence relationship of the magnetic field produced by a bar magnet can be measured through a simple experiment that closely matches the predicted proportionality relationships set by Baird-Savart's law, and the experimental measurement of the magnetic field off-axis is challenging as many potential sources of error are involved.